represent a graph. So you represent a graph either in the form of an adjacency list or an adjacency matrix. Okay, so let us see the undirected case first and then look at the directed graph. So in the case of a list, you just maintain the neighbors for each node. Okay, so you have, say, an entry for each node. So it could be like if you really want to implement an array of linked list, so you have one entry for each node, so that's the index to the array, and then each entry index will have a linked list containing the list of neighbors. So for node 1, of course, we can maintain an order. We'll maintain the neighbors in the increasing order of their IDs. So 3, 4 and 5 are the neighbors for node 1. For node 2, 4 and 5 are the neighbors. For node 3, 1 and 4 are the neighbors. For node 4, 1, 2, 3 are the neighbors, and so on. Now, in the case of a matrix for the undirected graph, you have a square matrix, one entry for one row entry for each node and one column entry for each node. And it's a binary matrix. You have either a 0 or 1. And you have a 1 if there's really an edge between the two vertices. So there's an edge between 1 and 3, so that's why you represent it as a 1. There's an edge between 1 and 4, so you represent as a 1. There's no edge between 1 and 2, so the entry is a 0. There's no edge from 1 to 1 or between, so the entry is a 0. And most of the times we'll have the diagonal to be 0, unless there's something called a self loop. Self loop means there's an edge from a node to itself, say from 1 to 1 or 2 to 2. The entries for the diagonal will be 0 in the adjacency matrix. So that's for the undirected graph. Now for the directed graph, we have to follow a convention. Before that, I'll tell you, introduce a couple of terminologies. So in the case of undirected, we just said neighbors, right? So 1 and 5 are neighbors. Whereas in the directed graph, we cannot say 1 and 5 are neighbors as it is. We have to consider the direction too. So we say node 1 is what is called an outgoing neighbor for 5. So this edge from 5 to 1 can be called an outgoing edge, okay, because it leaves 5, it goes out of 5 and it goes to 1. So from node 1's point of view, this edge can be called as an incoming edge. So the edge from 5 to 1 is called as an incoming edge. So the same edge is an outgoing edge for one vertex and an incoming edge for the other vertex. Okay, so we have to follow one convention, whether you want to represent the outgoing edges in the adjacency list and adjacency matrix, or you want to represent the incoming edges. You should not mix up both. So if you represent one, automatically the other will be captured. Okay, so in this figure here, I am capturing the outgoing edges, and that's the convention we typically follow. And there's something wrong in capturing the incoming edges. You will eventually get the same answer. But just as a convention, we'll follow the outgoing, represent only the outgoing edges. Okay. So for node 1, the outgoing edges are 3 and 4. So those are the two vertices you list as the neighbors. So they're really the outgoing neighbors for node 1. Now node 2 does not really have any outgoing neighbors, so its list is empty. Similarly, node 3 does not have any outgoing neighbors, so its list is also empty. Whereas node 4 has 2 and 3 as its outgoing neighbors, and node 5 has 1 and 2 as its outgoing neighbors. So that is how you capture the edges in a directed graph. Similarly, in the matrix, you represent the entry as a 1 if there is an outgoing edge from the row vertex to the column vertex. So there's an edge from 1 to 3. That means row 1, column 3, you have a 1. There's no edge from 3 to 1. So that means row 3, column 1 will be a 0. Okay, so again follow a convention. So once you fix the convention and run the algorithm, things will not will be messed up. But if you mix up things, sometimes for some entries you store the outgoing neighbors, some other entries you store the incoming neighbors, then your answers will not be right. Okay, so follow one particular convention and stick on to that. So as I said, there's no edge from 3 to 1, so we are maintaining the originating vertex as the row enters. So there's an edge originating at 1, which is outgoing at 1, that also means the same, and there's an incoming edge or ending at 3. So that's why we use the outgoing, the starting from which vertex as originating vertex as the row entry, and the ending vertex or the terminating vertex we can call as the column entry. So there's an edge from 1 to 3, so the entry for row 1 column 3 will be a 1. Similarly, there's an edge from 1 to 4, so the entry for row 1 column 4 will also be 1. Now there's no edge from 1 to 5, even though there's an edge from 5 to 1, that should be captured here. The edge from 5 to 1, outgoing 5, incoming 1 is this entry. Whereas there's no edge from 1 to 5, so row 1 column 5 will be a 0. Okay. Any question on this? Good. So let me see what time. Okay, we can run through this some more time. All right. Now the adjacency matrix or the edges, first of all, the edges could have some weights. So in the previous examples we have not seen weights so far, but you could have some weights for the edges. The weights could represent depending on what you model. So for example, if this is a network of cities, the edges represent, say, the roads between the two cities. There's a road, say, between node 1, edge city 1 to city 3 of distance, say, 8 miles or 8 whatever the unit, okay, or it takes 8 hours to travel from city 1 to city 3. So it depends on how you model. You have to clearly define how you model it. So similarly, between city 1 and city 5 it may take 3 hours to travel, and so on average again. So that could be one thing, the number of hours it takes to travel between cities, or it could be the number of even airports, the number of hours to take to travel between two airports, or the distance. So you see, that's where the abstraction comes. So once you get the node and edges, you can write down even the weights for the edges, and the same edge graph, the edge weights could be written to indicate different things. Okay, so you don't have to really draw different graphs for different representing different weights. Okay. Similarly, the adjacency matrix, once you get the graph, now previously if there's an edge between two nodes we had a 1. Now here instead of the 1 you put the weights, that's all it is. So from between 1 and 4 there's an edge of weight 5, you represent that 5. Between 1 and 3 there's an edge of weight 8. Now this is undirected graph. Now one thing you should also notice here, for undirected graph, the adjacency matrix will be symmetric in nature. Symmetric means the upper triangle will be same as the lower triangle. So what it means is you have the entries like 0, 0, 1, 1, 1 for node 1. That means node 1 has an edge to 3, an edge to 4, and edge to 5. That also means node 3 has an edge to 1, node 4 has an edge to 1, node 5 has an edge to 1. So the column will also have 0, 0, 1, 1, 1. So when you have row 0, 0, 1, 1, 1, the column is also 0, 0, 1, 1, 1. Similarly for node 2 you have 0, 0, 0, 1, 1. The column for node 2 is also 0, 0, 0, 1, 1. Similarly node 3, 1, 0, 0, 1, 0, node 3, 1, 0, 0, 1, 0. So this is a property of a symmetric matrix, and undirected graphs, the adjacency matrix is a symmetric matrix. Whereas for a directed graph, the adjacency matrix will not be a symmetric matrix, most likely need not be. So you have, say, for node 1 entries like 0, 0, 1, 1, 0. We don't really expect that to be for column 1, 0, 0, 0, 0, 1. That's different from what you have for row 1. So in the case of weighted graph, which is an undirected graph, you again have the symmetric matrix property for the adjacency matrix. So you have 0, 0, 8, 5, 3, 00853 for node 1. Node 2 00072, you have 00072. So that symmetric property will be carried over even if the graph is a weighted graph. Okay. So unless I mention any weights for the edges, the edge weights are considered to be 1. Alright. Okay, so let me stop and save this video.